Hello students, welcome back to another video lectures on the topic that is free falls of this chapter's gravitational. In the previous video we have discussed more about the gravitational. We have also learned some numerical problem, but in this video we will discuss only the free fall, okay, and the calculations of acceleration due to gravity. So the first topic is a free fall. Okay, what's the free fall says? Okay, now you see you're standing in the height of the building. Okay, you didn't throw the ball, but if you just drop it, okay, you didn't blindly fall, but you drop it. You keep the stop and you drop it, right? That stop, whatever it is, you didn't throw like this. You haven't thrown the ball in this direction, right? You haven't thrown the ball, but you just have left the ball, okay, or any stuff, or any materials, any substance, or any object, okay. So when you throw, it get pulled down, okay, it get fall downward. Why does it fall? Okay, why does it fall? And that fall is what we call as a free fall. You are not applying a force on it. Okay, you just left. Let's see, I will just take an example. I'm just holding a markers out here. I'm not throwing down. Okay, I'm leaving this. Okay, I'm leaving this. So when I leave this pen, it fall on the ground. Why? Okay, and that falling, the process, that is what we call as a free fall. What does free fall say? Okay, the free fall, you see, the free fall is due to the attractions. Okay, the object falls toward the earth. The object falls toward the earth under this force. Okay, under the force, that is what we call gravitational force. The earth, whenever the object falls toward the earth due to the gravitational force, that object, okay, that object which falls toward the earth is what we say the free fall. Okay, so that is what we say the free fall. Let's try to calculate more about these things. Okay, you have known what is free fall. Okay, then let's try to find out the relation between the free falls and all the. Let's try to find out all this formulas and the derivation based on free fall. So before this, let's try to take the example. Now let's say one boy stands out here and trying to throw the ball from here, trying to leave the ball from here. Okay. Another one more boy is standing here and trying to leave the ball from here. Okay. The same ball, the balls are identical, means same mass. Okay. They have the same mass, but their heights are different. Okay. One is a bit at the top and another is a bit lower than this one. Okay. Now, suppose you are standing on the ground. Okay. Suppose you are standing on the ground and you're asked to collect the ball from here, or you collect the ball which is thrown from here. Do you know which one will be difficult for you to collect? Okay, this is amazing that one is throwing from this very top of the building and another one just on the roof of the roof of your house. Which one will be difficult for you to collect the ball? There's always that. Okay, the one which is very high. The one which is very high, okay, the one who is standing in a very high, if you throw the ball from there, it will be very difficult to collect the ball. Am I right? But the one which is nearby to the ground levels, it becomes very easier to collect the ball. Why? The question becomes why. Why it has become difficult to collect? The same ball is the same identical, same mass. Okay, but when the object is thrown with very height, but when the object is thrown from the lower height, okay, the one which is the higher height becomes difficult for us to collect the ball. Why? Okay, you see, whenever the object fall from the higher, okay, they experience an acceleration. They experience the what? Accelerations. Okay, now what is an acceleration? Acceleration is what? A rate of change of velocities. Okay, the velocity keep on changing after 1 second. Okay, and velocity keep on changing after 1 second. You see, while falling, there is no change in the direction. Whenever you are falling the object, whenever you are trying to fall down the object, there will be no change. The object will not go toward this direction, the object will not go in this direction, so neither the object will go in this direction. The object, whenever you are trying to fall it down, the object will go downward toward earth. There will be no change in the direction, but there will be always a change in the velocities. Okay, why? Because they experience the acceleration. Okay, you see, while falling there is no change in the velocities, direction of the object of the or motion, direction of the motion of the object, but due to the earth attraction, there will be a change in the magnitude of the velocity. Okay, magnitude in the velocities. Okay, so why does the change in the velocity is? Why does there is a change in velocity means why the object experience an acceleration? Change of velocity means what? The object is experiencing an acceleration. Am I right? The object is under the acceleration. If there is a change in velocity, means the object is under the acceleration. The object is experiencing the acceleration. Okay, why this happen? Okay, we have learned in the Newton's second law. Okay, Newton's second law is as a force is equal to mass into acceleration. Okay, so that means what? If the mass is there, if the acceleration is there, that means there will be a force. Okay, if there is a force and if there is a mass, then there will be an acceleration. Okay, that means what? The object is been experiencing a force. Okay, the object is been experiencing a force. But you see, the one who is standing in this direction, he doesn't throw like this. He didn't put any force. He just let it. He just leave the ball, right? He just leave the object. He didn't exert any force. But from where this force came? This force is due to the gravity. Okay, the force is due to the gravity, and the acceleration is due to the acceleration due to gravity. This acceleration is due to the gravity. Acceleration due to gravity, and the force is what? And this acceleration due to gravity is always denoted by small letter z. Okay, this acceleration is what? From where this acceleration? The object that experiences acceleration is due to the gravity. Okay, so this acceleration due to gravity, that is g. Okay, so from where this experience come? From where they experience a force. Okay, from where they have exerted force, the force is due to the earth gravity. Okay, the force is due to the gravitational force. Okay, so acceleration is due to earth gravitational force, and therefore the acceleration is called the acceleration due to the gravity. Okay, whenever there is a force, there will be an acceleration, there will be a mass. That means object will experience the mass, object will be having a acceleration. Okay, so that is what we have learned in the previous previous chapters. That is force and emotions. Okay, force and emotion. That is what we learned in the Newton's second law. Okay, so from here, if I want to write the force due to gravity is equal to what? Mass into acceleration. That is g. Okay, mass into acceleration, that is g. Okay, mass into acceleration, that is g. Now you see, we have also learned in the universal law of gravitation. Let's try to make it more clear about this one. Okay, let's try to make it very clear about this one. First is what we learned: force is equal to mass into gravity. Mass of an object into gravity. Now let's say this is our Earth. Okay, now our Earth, the object, whatever we are taking is on the surface of the Earth. The object is falling, let's say this is from here. The object is falling in this direction. Am I right? Okay, the object is falling in this direction. Let's say this is our height. Okay, let's consider it to be the surface of the Earth. Okay, so we cannot actually experience in the 3D. So let's say it is the surface of the Earth. Okay, now you see, we have learned that in the universal law of gravitational, we have learned that what is the universal law of gravitational said. Okay, in the entire universe, okay, between the two objects, there experience a force. Okay, that means the force will be directly proportional to the mass product of the masses and inversely proportional to distance. Okay, so we have learned that whatever the force applied, let's say this is a mass m and this is a mass capital mass of its Earth. Okay, now the distance between the object will be considered as the diameters or radius of the Earth. distance between the two objects will be considered as a radius of the earth. Okay, that means what? According to this is our equation 1, and according to gravitational law of force, we have learned that G is equal to what? G is equal to mass of the earth into mass of the object divided by distance between the two objects, that is the radius of the earth. We'll assume that the distance between the two objects is what? It's the radius of the earth. Why? Because whatever the fallings of object is taking place on the surface of the earth. Okay, so this is the radius of the earth. Now this is our equation. Okay, so both these forces are equal to each other. Okay, since from equation 1 and 2, from equation 1 and 2, okay, so we got what? mg is equal to what? G and capital small letter m divided by r. And this small letter m and this small m, that is the mass of an object, are been cancelled. So what is you got? The gravity is, the acceleration due to gravity is what? M is equal to, this is what we are getting. Okay, so this is our G. This is how we find. Okay, by putting the values of the mass of an earth and the radius of the earth and the gravitational constants, okay, we get the values of G. Okay, the SI unit of G will be mass in the meter per second square. Why? Because it is acceleration. You know, like as unit acceleration that we define the accelerations of the earth, we define similarly as mass into accelerations. Mass into mass meter per second. The SI unit of what is it? Gravity is our acceleration due to gravity. This is what we call G. The small g is what we call acceleration. Acceleration due to gravity. Due to gravity. I told you in the previous video lectures also, don't get confused with the capital G and a G. Okay, so acceleration due to gravity. Okay, the SI unit of this acceleration due to gravity is what? Mass into, meter per second square. Acceleration due to gravity, the SI unit of acceleration due to gravity is what? Meter per second squares. Okay, so I think you're clear about this one. Okay, I think you're clear about this one. What is how can we derive the G? Okay, G is equal to what? G is equal to what? The small letter G, that is acceleration due to gravity, is equal to the product of gravitational constant in the mass of the earth divided by r, that is the radius of the r. Okay, so since earth is not a perfect sphere, okay, as the radius of the earth increases from the pole to the equator, the values of G become greater at the pole than at the equators. Okay, so what does it mean? You see, our earth, you know, the shape of our earth, it is not a complete, it is not a perfect sphere, right? It's like an oval. Okay, so our earth is something like this. Our earth is something like this, not exactly like a sphere, if I'm not wrong. Okay, it is not like in a sphere. Okay, so our radius from here, it will be more in the equator than to be in the pole. Am I right? Am I right? Yes. What is it? Our earth, you see, radius of the earth increases from the pole to the equators. Okay, the radius of the earth, okay, this is our pole. We know this is a pole, right? Pole, north poles and south pole we have learned. Okay, this is our equators. Okay, so radius from this, the center from here to here, okay, they are quite different. From the radius, from the pole to the equator, the radius keep on increasing. Okay, so the more the radius increases, okay, the more the gravity is also, the gravity due to acceleration also increases. That means what? A gravitational due to gravity, okay, acceleration due to gravity will be more, acceleration due to gravity will be more in the equator than in the pole. Okay, that means acceleration due to gravity will be more in the equator than in the pole. Okay, so the more the equators, if the distance increases, that means acceleration due to gravity will be reduced. That means what? The more, if the distance is far, that means acceleration due to gravity will be reduced. Okay, that means what? If as the radius of the earth increases from the pole or to the equator, the values of G become greater at the pole than at the equator. So that is what I told. Okay, so what is it? The pole will have more acceleration due to gravity than the pole. Then the gravities of the acceleration will be less in terms of equators. Okay, so what does it mean? Okay, accelerations of gravity. Remember this one. Acceleration due to gravity will be more. Okay, will be more in pole, okay, then equators. Okay, the acceleration due to gravity will be more. That is what? The more the distance, the more we keep far from the distance, the acceleration due to gravity will reduce. Okay, so the more the distance far away from the Earth, then mass it will be less acceleration due to gravity. I think you're clear about this one. Am I right? So let's try to solve the values of the. Let's try to find out the values of the G. We know that the values of the capital G is what? 6.673 into 10 to the power minus 11, right? 6.673 into 10 to the power minus 11. Okay, so we know that. Let's try to find out the values of the. We know that what is it? Let's try to find out the values of the G. Okay. So our here is our G's. We know what is G. G is capital G into M, capital M divided by R squares. And we know G is what? Capital G is what? Capital G is what? Gravitational proportion constants. Okay. And the values of this one is what? 6.673 into 10 to the power minus 11. Okay. What is it? SI unit is what? SI unit is what? Newton meter squares per kg squares. Next, we have a mass, that is M, that is a mass of the Earth. And mass of the Earth is taken nearly to be 6 into 10 to the power 24 kg. Okay, mass of the Earth is nearly taken to be 6 into 10 to the power 24 kg. Okay, next we have a radius. Okay, R. The Earth. Let's take this one as a capital R. That is the radius of the Earth. So radius of the Earth. That is radius of the Earth. Okay, radius of the Earth. Okay, radius of the Earth will be nearly equal to 6.4 into 10 to the power 6 meters. Okay, so this is what our radius of the Earth, and these are all the units. Now if I put the values of G, okay, 6 is what? 6.673 into 10 to the power minus 11 into M is what? 6 into 10 to the power 24 kg divided by what? R is it? 6.4 into 10 to the power minus 10 to the power 6 squares. Okay, so calculate all this. If you calculate all this, divide and subtract all this, you will get 9.8 meter per second squares. Okay, you will get the values is what? The values of the G is what? 9.8. So the values of the G is what? Nearly 9.8 meter per second squares. I think you're clear about this one. Okay, I think you're clear about this one. Am I right? So this is all about the free falls and the values of the gravities. Okay, so motions of the object under the influence of gravitational force of the Earth. Okay, motion of object under the gravitational force of the Earth. You see, we know that the object experience, okay, acceleration due to the free falls only. Okay, we know that what is the object experience and acceleration during the free fall only. Okay, whenever the object falls, okay, whenever the objects are under the free falls, okay, the object experience an acceleration. Okay, this acceleration experienced by the object does not depend on its mass. Okay, the object which is experienced, okay, the acceleration which is experienced by the object, okay, which is influenced under the acceleration, does not depend on the mass. Okay, this means that all the objects, either hollow, solids, okay, big or small, should be fall on the same rate. Okay, it should be fall on the same rate. Okay, that means the object will fall in the same rate, that is 9.8 meter per second. Okay, 9.8 meter per second they will fall on this acceleration only. Okay, so you see, there was a great saying that Galileo, okay, he was the first scientist who tried to drop the different stuff from the leaning towers, okay, leaning towers of Pisa in Italy. Okay, he tried to drop all the substance like hollow, light, every small, big from the leaning towers, okay, in order to prove that whether they are same or not. Okay, so he have proved it. Okay, so as the G is constant near the Earth, all the equation for the universal acceleration motion of the become valid with accelerations A replaced by the G. Okay, so this is what we have learned. Okay, so this is what we have learned, that whenever object falls, okay, whenever the object is under the free fall, the object falls, okay, the object will experience an acceleration. And whenever the object experiences an acceleration, remember that object does not depend on the mass. Okay, that means whether object may be hollow or whether object may be solid or big or small, they will fall on the same rate. That rate is what? 9.8 meters per second. Okay, so whenever the object falls toward the earth, the acceleration due to gravity is always taken to be negative. Okay, when the object falls toward the earth, the acceleration due to gravity is, okay, acceleration taken as a negative when opposed to motions. Okay, when an object falls toward, you see, the acceleration due to gravity will take always negative when the objects, okay, when the object, if the object is going from top to bottom to top, if the object is going from bottom to top, okay, you are trying to move up in the sky, but still the acceleration is exerting on you. Okay, so during the time, our g, the values of the g, is always considered as a negative. But if you are falling on this, okay, your acceleration will become 0, but we will only consider the accelerations of the earth. Okay, so this is all about the chapters. In the next video lectures, we will discuss about mass, weight, okay, weight on the object of the moons, okay, and then the thrust and the present in the next video lectures. Okay, anyway, right after this video lectures, we will be having a simple one class test. Okay, so be ready. Bye bye.